Hello, I am accountably-safe, and I will be talking about the availability-accountability dilemma and its resolution via accountability gadgets. This is joint work with my colleague Joachim Noor and my advisor David Che. So what is availability and what is accountability? To answer these questions, let's start with Bitcoin. Bitcoin was the first protocol to provide liveness under dynamic levels of participation. Bitcoin was designed for the internet setting, which is characterized by the fact that the protocol participants can come and go at will. An unfortunate feature of the internet setting is censorship. In this setting, the adversary can force a large fraction of the validators offline. Bitcoin provides stronger censorship resistance guarantees through its dynamic availability property. Another feature of the internet setting is the fact that the protocol participants are no longer just simple computers, but they are rather economic agents. These agents seek to maximize their profits. Thus, to align their incentives with those of the protocol, Bitcoin introduced block rewards. An ongoing trend in the blockchain space is the shift from proof of work to proof of stake. One major protocol where this shift is manifested best is proof of stake Ethereum. An observation behind proof of stake Ethereum was that the block rewards are not enough to align the incentives of the protocol participants. The reason for that is that the protocol participants could always benefit from safety attacks through double spends, etc. Proof of stake Ethereum introduced a finality gadget to sustain safety across network partitions. An added benefit of the finality gadgets was the fact that they could be used to provide accountability. Accountability, or in its longer form, accountable safety, states that if there is a safety violation, observers of the protocol would be able to identify adversarial validators that have provably violated the protocol rules. This enables the protocol, upon detecting the adversary, to impose financial punishments, such as slashing of its stake. Thus, proof of stake Ethereum provides stronger incentive alignment through not only the use of rewards, but also punishments for protocol violation. So far, we have identified two useful features for consensus protocols designed for the internet setting. The first one was dynamic availability. The second one was accountability or accountable safety. So how does Bitcoin and proof of stake Ethereum satisfy these respective properties? To answer this, let's investigate each protocol separately. In Bitcoin, miners propose blocks on the tip of the longest chain in their view. Even if a large fraction of the validators or miners go offline, the remaining miners would be able to extend the longest chain. Thus, Bitcoin provides availability under dynamic levels of participation, as liveness would not stall even when the large fraction of the validators go offline. However, let's now consider the case that the validators on the right-hand side were not in fact offline, but they were perhaps partitioned. In this case, the validators on the right-hand side could be mining a conflicting chain. This would indeed cause a safety violation in the view of the observers. So, a node that observes the system at this point would see two conflicting chains, yet would not know which party is faulty. In fact, in this case, there is no faulty party. This observation tells us that Bitcoin cannot provide accountable safety, since even in the case of a safety violation, it could be the case that every miner is honest. Now, let's look at proof of stake Ethereum and examine a similar attack. In the finality gadget of proof of stake Ethereum, validators vote for the blocks that are proposed at the tip of the finalized chain. Upon gathering a sufficiently large quorum of votes, these blocks become finalized. Now, let's consider an attack where two blocks are proposed at the same height. The intention of the adversary is to ensure that both blocks are finalized, and thus to have a safety violation. The honest validators vote for the first block they see at the site. In this case, the block on the left-hand side gathers a larger quorum of votes, thus becomes finalized. On the other hand, the block on the right-hand side is not finalized. Observe that adversarial validators can violate the protocol rules by double voting for the two conflicting blocks. In this case, the block on the right-hand side would also become finalized, causing a safety violation. Upon seeing this safety violation, observers of the system could inspect the votes. After inspecting the votes, they would notice that a fraction of the votes, those by the adversary, might have been double votes for the conflicting blocks. Thus, these observers would be able to identify that these adversarial validators have irrefutably violated the protocol rules. This is the property that we call accountable safety, or accountability for short. Although the finality gadget of proof-of-stake Ethereum can provide accountability, unfortunately, it cannot provide availability. Let's again consider a block that was proposed at the tip of the finalized chain. In the event that a large fraction of the validators go offline, the votes from the remaining validators might not be sufficient to finalize this block. In this case, the finalized ledger would stall. Thus, there will be no liveness over periods of low participation. This shows us that the finality gadget of proof-of-stake Ethereum cannot provide dynamic availability. Now, is this dichotomy particular to Bitcoin and proof-of-stake Ethereum? Is it true that no protocol can provide both properties simultaneously, or is there any protocol that can achieve both of them at the same time? Unfortunately, the answer to this question is no, as stated by the availability accountability dilemma. To prove the dilemma, for the sake of contradiction, let's assume that there indeed exists a protocol that can satisfy both dynamic availability and accountable safety. Let's consider the universe where this protocol is deployed. In this universe, the validators on the left-hand side are honest, whereas the validators on the right-hand side are adversarial. Each validator can talk to each other within their respective groups. The honest validators attempt to contact the other validators. However, the adversarial validators pretend like they do not hear anything from the other validators. And in return, they do not send back any messages. Thus, from the perspective of the honest validators, it looks like they are isolated and everyone else is forced offline. Let's consider two clients, Alice and Bob, that are trying to learn about the latest consensus messages. Upon contacting the validators, Alice would hear back from the honest ones. The honest validators would tell Alice that they did not hear back from any other validator, so these other validators must probably be offline or forced offline or censored. In this case, the honest validators would tell Alice to decide A as the consensus decision. On the other hand, upon contacting the validators, Bob will hear back from the adversarial ones. The adversarial validators will tell Bob they also did not hear back from the other validators, so all other validators must probably be also offline. These adversarial validators, however, would tell Bob to output B as the consensus decision. We have assumed that this protocol satisfies dynamic availability. Hence, even over periods of low participation, these clients should be able to output a consensus decision. As a result, they would trust their respective validators, in which case the Alice would indeed output A as its consensus decision, whereas Bob would output B as the consensus decision. Observe that this is a safety violation. We have said that the protocol satisfies accountable safety. And accountable safety states that when there is a safety violation, the clients will be able to identify an adversarial validator to have irrefutably violated the protocol rules. Thus, to conform to this property, we would assume that Alice and Bob together would identify an adversarial validator from the group in the right-hand side. However, notice that this universe of configurations is indistinguishable in the view of these clients, Alice and Bob, from the universe that is currently on the screen. Thus, the previous universe where the left-hand side validators were honest is indistinguishable from the universe where the right-hand side validators are honest. As a result, when there's a safety violation in the second universe, Alice and Bob would again identify a validator from the right-hand side to have irrefutably violated the protocol rules. Unfortunately, the validators on the right-hand side are now honest, and identifying an honest validator for a protocol violation contradicts with the accountable safety property. Hence, we have reached a contradiction. And this contradiction implies that no consensus protocol can satisfy dynamic availability and accountable safety at the same time. So how do we resolve this dilemma? We have observed that a protocol that outputs a single ledger cannot satisfy accountable safety and liveness under dynamic participation simultaneously. Hence, instead of a single ledger, why don't we resolve this problem by having two nested ledgers, an available full ledger and an accountable prefix ledger. The available full ledger would satisfy safety and liveness under dynamic levels of participation as long as the fraction of online honest validators is high. On the other hand, the accountable prefix ledger would always satisfy accountable safety, and it will be live if the participation is high enough. The most important observation here is that these two ledgers are always consistent with each other. In particular, the accountable prefix ledger is always a prefix of the available full ledger. This consistency among these ledgers enables clients to choose the better guarantee for their transactions and yet avoid any conflicts with each other. For instance, a car dealer might find it prudent to wait until a transaction that pays for a car enters the accountable prefix ledger. This is because the accountable prefix ledger provides stronger guarantees against safety attacks and more specific ones such as double spends. On the other hand, a coffee vendor might find it sufficient to wait until a transaction that pays for a coffee enters the available full ledger. This is because for the coffee vendor, the speed or the low latency of transactions is a more important property than safety of each individual transaction. And most importantly, even though these clients want different guarantees, they will never conflict with each other. Thus, they could live in the same universe. Okay, so how do we achieve two nested ledgers that satisfy the properties of accountability and availability? We do this through the use of accountability gadgets. Accountability gadgets can be instantiated with any accountably-safe consensus protocol, as shown in the middle of this diagram. They are deployed on top of longest chain protocols. These longest chain protocols take transactions as input and output a sequence of confirm blocks. For instance, these confirm blocks can be the KD blocks on the longest chain outputted by the longest chain protocol. These confirm blocks are then outputted as the available full ledger. At the same time, these blocks are given to the accountability gadget, which treats them as proposals for checkpointing. Upon observing a proposal for checkpointing, the validators in the system would send checkpointing votes. These votes are then ordered with the use of the accountably-safe consensus protocol, with which the accountability gadget was instantiated. After the votes are ordered, a checkpoint decision is reached. Thus, a proposal becomes checkpointed or not. The prefixes of the checkpointed proposals or the checkpointed blocks on the longest chain are outputted as the accountable prefix ledger. These checkpoint decisions are also fed back into the checkpoint respecting longest chain. The name indicates that this protocol no longer treats the longest chain simply as the canonical one. Instead, it requires the longest chain to go through the latest checkpoint decision to be the canonical chain. Okay, let's see our accountability gadgets in action and observe how they provide availability and accountability for the full and the prefix ledgers respectively. In this example, we have 4 validators, A, B, C, and D. These validators propose blocks on the tip of the longest chain in their view. At this point, none of these blocks are checkpointed, so there is no accountable prefix ledger, and there is only the available full ledger. Occasionally, blocks on the available full ledger are proposed for checkpointing within the accountability gadget. Upon seeing a proposal, the validators vote for it. At this point, we have seen that the block number 5 has received enough checkpointing votes to become checkpointed. Thus, block number 5 becomes checkpointed, in turn checkpointing its prefix on the longest chain. We observe that since the block 5 is checkpointed, now the accountable prefix ledger catches up with the available full ledger. Now, note that some of these validators could be offline or forced offline by the adversary. In this case, the accountable prefix ledger might not make any progress. However, the online validators would still be extending the longest chain that goes through the latest checkpoint decision. Thus, the available full ledger would always keep growing, even when the participation is low. Thus, we observe that the available full ledger does indeed satisfy the availability property as claimed. Another useful property satisfied by this protocol is predictable validity. Predictable validity states that when a block is proposed, the prefix of the block that is seen by its proposer would not change after the block becomes confirmed, after the block enters either the available full ledger or the accountable prefix ledger. This property is especially useful for applications like light clients and sharding. Finally, let's observe a safety violation on the accountable prefix ledger and see and witness how accountability is satisfied. For this purpose, let's assume the validators C and D are adversarial. It could be the case that these adversarial validators, or rather the honest ones that have not observed the latest checkpoint decision, maybe due to network partitions, could be mining a longest chain that conflicts with the latest checkpoint decision. At this point, a block on that longest chain that conflicts with the latest checkpoint decision, for instance, block 3 that conflicts with the latest checkpoint block 5, could be proposed for checkpointing by the adversary. Once this proposal is seen by the validators, of course, the honest validators that have voted for the conflicting checkpoint block number 5 would not vote for it. However, the adversarial validators and the honest ones that have not seen the latest checkpoint could vote for it. In this case, block 3 that conflicts with the latest checkpoint block 5 also becomes checkpointed. Now, as a result, we see a safety violation on the accountable prefix ledger. However, the accountability property states that whenever there's a safety violation on the accountable prefix ledger, the adversarial validators would be identified to have irrefutably violated the protocol rules. True enough, by inspecting the double votes on the conflicting checkpoints block 3 and block 5, we will be able to identify the adversarial validators C and D. Thus, our protocol does indeed satisfy accountability for the accountable prefix ledger. We have also implemented our protocol using HotStuff as the accountably-safe consensus protocol. The accountability gadget was deployed on top of a longest chain protocol, and experiments were run. We have benchmarked our experiments against Gasper, the consensus protocol for proof-of-stake Ethereum. two major metrics of comparison for us were the average bandwidth requirement measured in watts per second and the average latency for the accountable prefix ledger. We observed that for the same bandwidth and latency requirements, our protocol can accommodate twice as many validators as Gasper. Thus, it can achieve a higher degree of decentralization under the same network settings. On the other hand, when bandwidth requirement is fixed, we observe that our protocol can achieve twice as small a latency for the accountable prefix ledger as Gasper. We observe that the same property holds true for different bandwidth requirements. Thus, our protocol can outperform Gasper in terms of latency and decentralization. Finally, I would like to conclude by comparing our accountability gadgets with some related work. One major axis of comparison is the versatility of the protocols that were used to construct the finality and accountability gadgets. We have seen that accountability gadgets can be instantiated with any accountably-safe consensus protocol, and they can be deployed on any Nakamoto-style longest chain protocol, including proof-of-stake longest chain protocols. On the other hand, the finality gadget for proof-of-stake Ethereum is necessarily tied to Gasper FFG. In a similar vein, many of the finality gadgets deployed by industrial projects use handcrafted finality gadgets. The same holds true for checkpointed longest chains, which uses Algorand BA as its finality gadget. Thus, these other protocols do not provide the same versatility as accountability gadgets. We also observe that the checkpointed longest chain, the analysis of the checkpointed longest chain uses proof-of-work longest chain protocol, whereas accountability gadgets analysis holds for proof-of-stake longest chain protocols as well. The second axis of comparison is accountability. We have observed that accountability gadgets provide accountability. On the other hand, accountability is not a major goal for many of these finality gadgets, which are designed to preserve safety over periods of network partition. The same holds true for the checkpointed longest chain, and in particular, Algorand BA was shown to not be accountable. Thus, checkpointed longest chains cannot provide accountability as well. Another axis of comparison is security. Accountability gadgets come with their security proofs. However, there are known attacks on Gasper, the consensus protocol behind proof-of-stake Ethereum, thus rendering it insecure. Many of the finality gadgets deployed by industrial projects unfortunately also lack proofs and sufficient arguments for their security. The final comparison is in terms of predictable validity. Accountability gadgets provide predictable validity, thus making it easier to use light clients and sharding applications on top of them. On the other hand, Snap and chat protocols, which were doing so far well in terms of accountability and security, cannot provide predictable validity. Thank you very much for listening to my talk, and you can find the details about the prototype implementation with HotStuff, the formalization and proof of the availability accountability dilemma, and the construction and security arguments of the accountability gadgets on the links provided below.